Good afternoon and welcome back again to the STS-133 pre-flight briefings. We're here now to focus on one of the items being brought up by Discovery to the International Space Station inside the permanent multi-purpose module, Robonaut 2, soon to be the first dexterous humanoid robot to visit space. Here to tell us about it, we have Rob Ambrose, the acting chief of the Automation, Simulation, and Robotics Division here in the Engineering Department at Johnson Space Center. We'll start with an overview and then take questions from the audience. Rob?
Thank you, Brandy. I'm here talking to you today about a project that we've been working on for about 15 years. So it's really the culmination of many people's effort, a terrific group of engineers that we call the Robonauts. We might think of a robot like Robonaut as the machine, but we really think of the people behind the robots as the real Robonauts. In the room today, we've got one of the latest units that we've built. It's Robonaut 2A, the first in the Robonaut 2 series. If you can take a look at it, if we can cut over to show you the robot. It's in the tuck and ready for launch position. R2B is the one that's currently packed and ready for launch in the same posture, preparing to go visit the International Space Station on board STS-133. I'm going to show you today some of the history that got us to this point and talk to you about some of the challenges that the team met and the future for what the Robonaut system will deliver for us. In addition to all the engineers that are behind the Robonaut team, robotics is a growing field. It's a potential future market for our country and the world. And there are a number of communities out there that are also looking to this launch as validation of the decades of research that have made things like Robonaut possible. So in a sense, while it might be just a single step for this robot, it's really a giant leap forward for mankind. The challenge that we accepted when we started the Robonaut project was to build something capable of doing dexterous, human-like work. And here at the Johnson Space Center, where we're very focused on human missions, the idea was that that robot would be doing that work side by side with astronauts. So from the very beginning, the idea was that the robot had to be capable enough, strong enough to do work, but at the same time, be safe and trusted to do that work right next to humans. If you move to the second slide, you'll see the history of, well, so there's our vision, our history for the Robonaut 1 project, going back to the first integrated products in 1998. A whole series of developments building the Robonaut 1A system. It started out as just a couple subsystems, an arm and a hand. By '99, we'd put the arm and the hand together with a head. And for the first time, we experienced dexterous telepresence, where we could really kind of step into this robot and reach out and interact with objects, and in particular, EVA tools. And at that point, we realized we really had something special, that this capability was possible and that it was within our grasp. The Robonaut 1A system evolved over a couple years. We added a second limb. We went upright with a torso and formed what we think of as an upper body for a Robonaut system. Then we commissioned the Robonaut 1B unit, where 1A had a lot of electronics in a rack. Off to the side, 1B's electronics were all integrated in its torso. And that opened up a whole new series of opportunities for making the robot portable, able to move around, not just requiring that work be brought to it, but that it could go to the work and do the work where it sat. We tried a number of lower bodies. There's a picture there of a Robonaut 1B with a leg, which would be appropriate for climbing on the outside of the space station, or for on the inside for that matter, plugging into work intersite fixtures. We also tried it on a Segway, and then there's a photo there of a four-wheel base we built called Centaur, which we named based on the fact that it kind of looked like the mythological creature, 4 wheels, not 4 legs, but with the upper body of a human. We took that out to the field and tested it working with natural objects like rocks and geological samples. We learned a lot of things about the upper body, the dexterity, the component technologies, system level redundancy, and made major steps forward in the software. We were partnered with DARPA, the Defense Advanced Research Projects Agency, and teamed with a number of tremendous research partners across the country: USC, MIT, University of Massachusetts, Vanderbilt, Rice, and other universities were all brought in and have contributed in many ways to the Robonaut software. But at the end of this series, we had a number of new ideas, and you could only incrementally upgrade a robot so much. We had some ideas for what Robonaut 2 would be, and we went looking for some external funding. If you could go to the next slide. We found a terrific partner in General Motors. They shared our vision for a robot that could do work, real work, and do it safely next to people. Kind of at the core of that idea is that we're not replacing people. It doesn't make any sense to build a robot that can safely work around people if there are going to be no people. It's really predicated on the idea that there will be people working with the robot. They liked that idea. They saw that as a part of their future of combining humans and robots working together, and they agreed to partner with us on the development of the Robonaut 2 series. To date, we've built 2 units. R2A is the one here in the room with us today, and R2B is the one that is packed and ready for launch on STS-133. We went through a similar buildup where we built the Robonaut 2 limb first, the right arm on R2A, and then we built the second limb in the torso, and then moved on to the second unit, R2B. When we were given the challenge to take a Robonaut 2 to station, we selected R2B as the more recent one, and initiated a whole series of tests and then redesign to qualify the R2B system for flight. At the bottom of that slide is a photo of R2, one of the R2 units, in a test chamber out at the White Sands test facility. This was just one of the many tests that the Robonaut system had to go through and pass before being allowed and be certified for use on the space station. In that particular test, the robot was put literally in an oven and baked at 120 degrees for about 4 or 5 days. And at the end of that, the air was extracted from the chamber and sniffed by a computer nose that found very little off-gassing, and the robot passed. It's very important when you put something like a Robonaut in an IV environment that you not off-gas, emit chemicals off of the system and pollute the environment. It turns out the Robonaut 2s are pretty clean. The Robonaut went through a whole series of additional tests, and it's been a great last 6 months or so getting it certified. Go to the next slide, please. Let me tell you a bit about the arm. Superficially, it's very smooth and padded. There are no sharps or hard points that could hurt a person. But that's really just the beginning of making a robot safe. At the core, in the muscles of every joint, are springs that make the system compliant. So if you go push on it, it feels soft. So if the robot's minding its own business and just basically turned off, and an astronaut were to bump into it, it would give a little, and it would not injure the astronaut. That's using a series of springs that we developed with sensors capturing the deflection of the springs in a concept called series elastic actuation. We've also developed a way to coordinate those springs, not just through an entire limb, but with 2 limbs, reaching out and grasping objects in common. Most robots can't do that safely because they're very stiff, and a very slight position error would produce large forces, and the 2 arms would damage themselves. Because these robots are fundamentally soft, we are able to program them to work together with multiple arms, and in fact work with humans holding the same object. So superficially, it's soft, padded, and safe. Mechanically, it is soft as well with springs. But deeper than that, it has 3 levels of sensing, sensors, electrical sensors, and software that can, in each of the 3 levels, identify forces that are being felt by the robot, decide if those forces are safe or not, and stop the robot. That 3 levels of safety was essential in convincing our payload safety review panel that this robot would be safe to work adjacent to astronauts inside the space station. Each of those 3 levels has a separate sensor pack, separate cable harness going back to a separate process running, monitoring those forces. And if there's ever a problem, the robot can either just stop and wait for the problem to go away or completely turn itself off. It's programmable so we can have different levels or thresholds at which it will either pause or completely turn off. That is at the core of every motion that the Robonaut system makes, and it gives us confidence that the robot will be safe working around us. I'm going to now play 2 videos, well, a combination of 2 clips. Go to the first video sequence that shows this paradox. We want to have a robot that's both strong enough to do work, and at the same time safe enough to do it right next to us. So the first part of this shows it handling a dumbbell. That's a 20-pound dumbbell. You can relate to what that would feel like if you were to reach out and pick it up. Unlike people, which tend to cheat, this robot will really do what the physical trainers tell you to do, which is to do the bicep curls nice and slow. So as the robot's doing it, because of your empathy and the monkey see, monkey do ability of the human, you can almost feel what that robot is feeling. You know what that would feel like curling that weight, and that's because that's the way humans work. We look at other humans and we can kind of know what it would feel like if we were them. That applies to this robot. It is so human-like. You have a good idea of what the forces are that are involved. You can kind of feel the burn, right, as it's doing that exercise. Humans have greater peak strength and peak speed than a Robonaut 2. For a robot to be your assistant, you really don't want it to move too fast. But a Robonaut has more endurance than a human. While it might not have the same peak strength or peak velocity, it can do things much longer. And that's what you would really want in an assistant. If you asked the robot to hold something and then you were going to work on it for a while, the robot would not complain if you asked it to hold it for 30 minutes in the same position. That is what you'd want in a good assistant. And unlike some people, it will put things back when it's done. Another very useful thing in having an assistant. When you're done with an object, it can put it back for you. So it's strong. You will not see most of the humanoids out there handling 20-pound dumbbells. Most of them don't even really have fingers. They do a lot of dancing, and we're fine with that. We could probably program a Robonaut to do dancing, but we're pretty sure no matter what dance move we would give it, it would always do the robot. For us, it's more about doing work, and that's why we really focused on the upper body. So here it's doing a sequence. It's running through some open space motion. And now Dr. Ron Diffler is going to step into its workspace. We call this the Hit Ron demo. And you see the robot stopped. It paused. It detected that Ron had gotten in the way. And then when he let it go, it continued on with its sequence. While it's pausing, it's applying a very light force. It's trying to catch up. And when it does, it goes back to the motions that it's programmed to do. So this is running at the core of the robot every single time it moves. If a person steps in the way and interferes with it, nothing dangerous is going to happen. The robot will just pause. And if you hit it really hard, it'll stop completely and turn itself off. So we have those 2 levels of safety. They're always running whenever a Robonaut is in motion, working with our astronauts. So move on to the next slide, please. I'll tell you a little bit about the hands. Within each finger, we've got tendons, and we have force control. We're able to sense tendon forces and map that to finger forces. We also have load cells on every phalange, every finger bone, so we can measure fingertip contact forces. We can also resolve the direction of those contacts, so we can understand and let the robot understand that it's made contact with an object, and even use those fingers kind of like sensors to map out the shape of an object. You'll see how that's important in a minute. We've mapped those tendons and tip force sensors into whole finger control modes that allow the robot to be given different things like a soft grasp or a hard grasp, power grasp, and lots of different shapes of grasps that humans just really take for granted. This hand is a mechanical marvel. It's a mechatronic marvel because it's integrated with electronics as well. It has some things that humans just take for granted, but that you don't see in a lot of robot hands. It actually has palms. Most robot hands only have grippers that grab things between fingers. They don't envelop objects and bring them into a palm. The second thing that this robot has that's unusual is a soft covering. We take that for granted. As humans, we have skin, and sometimes we put other layers on called gloves. If you look at most robot hands, they're hard steel fingers. You would not ever want them to grab an object and then have an astronaut grab that object later. If it was an object that was made out of aluminum or steel, those hard fingers might leave a burr or a nick on that object that could later cut the astronaut's glove. What we want is to have a robot that does not cause nicks and burrs in the environment and will be safe to handle the same objects that we'll ask astronauts to handle. The skin is also really important for friction. We can put different kinds of materials in and give the robot's skin, palmar surfaces of the fingers, different levels of, different coefficients of friction to allow it to grasp objects more completely. And also a little cushioning, gives some give, and allows the robot to have both a very delicate, fine force resolution, yet still be tough enough to really get a white knuckle grasp on an object. I'm going to show you a couple video clips here that demonstrate how we take advantage of that. So play the next video, please. So this shows the robot hand kind of groping an object. It's a flexible material that's got a bump in it. The robot is basically scanning the object, using its sensors to map out the 3D shape of that object. It wouldn't need to do this every time, but once it's learned the feel of the object, it could apply that. So it grabs the object, it immediately knows where it is, and can now put its thumb in that divot. By having first familiarized itself with the object, it's able to now do that automatically. When it just first makes contact, to immediately know where it is and slide its thumb into position. As far as we know, this is the first robot that has that capability. Okay, next slide, please. Oh, okay. Oh, well, that's fine. We can play this video. So now, we're now going to talk about the future for the Robonaut system. This is the very recent past. The Robonaut 2B system was processed at the Kennedy Space Center, being prepared to be packed in the MPLM. So this is a time-lapse video showing the technicians, both Robonaut engineers and the Kennedy workforce, integrating the robot in its packing container that's then loaded inside yet another packing container for launch into space. And you can imagine after 15 years working on the project, how excited the engineers were to participate in getting to load up this robot and prepare it for a ride into space. It's in that same tucked position like the R2A is here in the room today. The station team built a terrific protective cage that packs the robot in foam, and then that box itself, as you'll see, is encapsulated in another layer of foam. And we didn't skimp on the screws. Now there's actually a couple other robots involved here. That one's a crane. People don't normally think of it as a robot. But the next one you'll see, most people would probably call it a robot. It's a very large machine that's going to reach out and grab this box. So there the Robonaut box is being encapsulated in yet another layer of foam. And now this enormous robot arm is going to pick up the little robot and pack it inside the MPLM. Okay. So you can imagine trying to reach into a canister like this would really ruin your back, but that giant robot arm has no problem. If you've ever tried to load a pickup truck, you'd know why you want this robot. And that's as we left it, ready for launch. I'd like to show the last slide, which shows some potential future applications. Obviously, we're very excited to get R2B sent to station. We've been working on some other lower bodies that are of interest for future applications. We'd like to add legs to the R2B system so that it could climb around on the inside of the space station. Again, we don't want to just have to bring work to it. We would like, once we've shown the robot's ability to do work, to free it up to climb around on the inside of the station and go to where the action is, solving problems for the crew. We've identified a number of tasks that we think are appropriate for the robot. It's being shipped with a task board. That's basically a test apparatus that has a lot of different interfaces on it. It has switches and latches and valves and triggers and various EVA and IVA interfaces that the astronauts use on a daily basis in space. And we're going to practice using the Robonaut 2 system on each of those interfaces. We have a similar system here on the ground, and we will, of course, try everything first on a ground robot. But the questions remain as to how the robot will work in zero gravity. Will all those interfaces work the same when there's no gravity load on the robot? And we'll compare the gravity results with the zero gravity results from the robot in space. We're also looking at some surface applications. We've got a new wheeled base that we've developed called Centaur 2, an upgrade to the ride we built for the Robonaut 1 series. The Centaur 2 was recently taken out to Desert Rats, one of our analog field test programs, where I was given a shakeout cruise. And that base, shown there in the center, really proved its mettle. It's going to be a fantastic little rover for the Robonaut to ride on, and might be the precursor robot of the future, able to go out ahead of astronauts and explore worlds before the humans get there, assist astronauts when they're there, and or maybe be left behind as a caretaker. We're also looking at legs and other wheeled bases that might be appropriate. And throughout the history of the Robonaut team, considering lots of different lower body options has been our philosophy. It's allowed us to adapt the system to different kind of worlds, different gravity levels, and find the right mobility for the application. But at the same time, allow us to stay focused on the upper body, the part of the Robonaut that really does the work. Because that's what the Robonaut program is all about. We have one last video. It's kind of a vision of the future. We would like to take the Robonaut 2 system outside once we add legs to the system so that it can climb. We would like to go outside with the Robonaut and help the crew with EVA tasks, just like it'll be helping with IVA tasks in this coming year. If we could play that last video. So pretty amazing rock climbing, right? Zero-G rock climbing, but you'd still like to have a leg or some kind of stabilizing appendage to free the hands to do work. Because we've certified it for indoor work with toxicity and flammability certifications, we've really built an indoor-outdoor robot. So it might just go in and out through the airlock like the astronauts do. But unlike the astronauts, it could be left out indefinitely and available for emergencies like patching leaks or other emergencies that have to be dealt with immediately while waiting for astronauts to go EVA and come out to help. So that's been the vision for the Robonaut system, working safely with humans for over 15 years. It's a dream come true to get to launch one. I can't tell you how excited we are. All of the Robonaut engineers have looked forward to this day for many years, and I applaud them for their patience and persistence and all the hard work that's gone into making this possible. At this point, I think we're ready for questions.
Okay, we'll start here with questions here at the Johnson Space Center, then take questions at other centers.
Hi, Robert Perlman with CollectSpace.com with a couple of questions. First, given how packed up it is and multiple layers of foam and screws and such, how long will it take the astronauts to unpack?
We think a couple hours should unpack the system. There'll be a lot of screws they have to keep track of, but it's not that hard to unpack it.
And with the example that was given on the hit and dawn, I guess.
With the what?
Hit dawn example.
Hit Ron, actually.
Ron. Okay, Ron.
Right?
Ron was on Earth with gravity anchoring
Right.
him to the ground. If an astronaut was free floating and an arm were to come in place, does the small pressure that you mentioned, does that have enough force to push the astronaut back?
So this is one of the things that we're going to be experimenting with. On Earth, we've set the thresholds where it will pause at just a couple pounds, and then thresholds for it completely safing itself a little deeper than that. But those forces are kind of biased by all the gravity loads that the robot feels. When we get into zero G, all the gravity loads go away. So if it feels a contact, it feels loads, it's really contact. So we should be able to dial down those thresholds to an even finer level. So we can't simulate that on Earth. We don't really have a zero G chamber. So it's part of the reason we have to do this in space is to experimentally lower those thresholds and make it finer and finer to see how low we can go. How light of a force could the robot detect and still pause? That's one of our experimental objectives. On Earth, we're on the order of like 1 or 2 pounds to move it around once it's paused.
Mark Carreau for Aviation
Hey,
Week.
Mark.
Hi. Can you tell us what the plan is for unpacking Robonaut in terms of time frame? Will it happen on this mission or some weeks away? And what do you sort of anticipate being the first series of activities that you would do as far as testing or operating or shaking down or however?
Well, the crew are busy. We're scheduling when it will be unpacked. It'll be long after the shuttle has left. We're hoping for a good Christmas present around Christmas time, maybe early January. We have a whole series of tests that we would like to do. The first is just a power-up test and watch the levels and make sure that everything came up as we expected. And then a whole series of kind of incrementally turning on more and more parts of the robot and verifying that the robot is healthy and that the current levels are the same as they were measured at Kennedy right before it was packed. So a whole series of those kind of checkouts. The robot is designed with a base stanchion pedestal, so it can be set up pretty quickly, and the astronauts can set it up or leave it up at their disposal. Over this year, we've got a whole series of task board experiments. Once we've checked out the robot, we'll kind of work our way across the task board from some of the simpler interfaces to the more progressively complicated ones, finishing handling flexible fabrics, something that robots really don't do well, but that Robonaut is really well designed to handle. So we'll kind of progress our way across the task board. Then we've got a couple tasks that we've been thinking of that we would like to mock up on that task board. And here we'll probably want to take advantage of equipment that's already on station and have the astronauts bring it to the task board. 2 tasks that have been identified are both housekeeping tasks. For 20 years, I've asked people, if you had a robot, what would you do with it? And very consistently, I've asked that question, and of kids, I get 2 answers. They first say, I would like it to do my homework, and then the second answer is, and then clean their room. When I ask adults, they always say cleaning, and then they usually mention either kitchen or bathroom. Very consistently, I've asked that question, if you had a robot, what would you have it do, for over 20 years. And House cleaning is at the top of the list. So there are two that we're looking at. The astronauts have to wipe down the handrails inside the space station with some wet wipes once a week, just for hygiene reasons, not to pass germs and develop biofilms. What a great job for the robot. Where the astronauts might be able to do it in a Saturday morning, wouldn't it be great if the robot was just always doing that, working its way around the station, always kind of cleaning? Another is vacuuming the air filters. All the electronics racks have these air filters. So as they're bringing air through the racks to cool it, the filters capture particulates and keep it from going inside the electronics. The crew have to go around and pull out these air filters, and then with a separate vacuum cleaner, vacuum out each of those air filters. Another very tedious task. I'd much rather give the crew their Saturday mornings back. If we could let the robot do those housekeeping tasks, what a great thing to give the crew back. And I think it fits with terrestrial models for what robots should do helping people. We're looking for more tasks, though, and it might be the crew are our best source of ideas. I'd like to say that the STS-133 crew has been terrific in embracing Robonaut on this ride to station, and we've been working with some of the astronauts that will be working with it on station. They've got a great attitude, thinking about what the robot could do, embracing this new idea, and being very creative about applying the technology to future missions. I'm really looking to them to come up with the next tasks for what the robot could do. They'll be living with it. They'll have a lot of time with the robot, and I'm really excited about what they will come up with as experimenters.
Thanks. Could you just talk about turning it on? Do you turn it on once and leave it on forever, or do you turn him on, and if you do, how long does it take? And if you turn him off, how long does that take?
They come up pretty quickly. There's a console that looks remarkably like your laptop that is set up that is used to operate the robot. It comes up in just a matter of minutes, and it goes down much quickly than that. In an emergency, it shuts itself off instantly. But normally it takes a couple minutes to turn it off and bring its power levels down. We will likely bring it up and use it for a session and then turn it off. One of the things that we've always done with our robots is we've had an emergency stop switch that we've used to just be safe. Because of the 3 levels of safety software, we are not going to need to use that switch. So we're not going to waste an astronaut having to float there with their thumb on a button the whole time. We really trust the robot to do the right thing and to be safe. That said, the astronauts will be able to operate the robot, or conduct experiments with the robot, or just turn it on and let people in ground control run those experiments.
Eric Berger with the Houston Chronicle. So in a year or two, as you sort of get into shake out the robot and get to the experimental phase, what constitutes a mission success for you?
So we've kind of laid out an evolution where the robot will first demonstrate its ability to do tasks with its hands in 0G. For us, that will be mission success. But for the robot to really be useful, it will have to be mobile so that it can go around and do work. So from a technology standpoint, demonstrating the ability to handle all these interfaces in 0G is really our engineering objective. From a practical standpoint, having the robot really pay its own way, it needs to be mobile so that it can climb around station and do work wherever the work is found. So the evolution is this year it'll be mounted fixed on its pedestal. Next year we're looking to send up legs so that it could be upgraded to go mobile. And we would like the year after that to send up a torso upgrade, a computer upgrade in its chest to allow it to go EVA, allow it to go outside into the thermal vacuum environment of space. So that's the evolution. From a engineering standpoint, the 0G manipulation is really our primary objective.
And just a quick follow-up, could the legs and the torso, I mean, that's a pretty sizable thing, go up on a Progress, or how would you get that to
Yeah, there are a lot
station?
of options that we've explored. They would be smaller pieces than the whole robot, smaller packages. We've looked at Progress, HTV, ATV, and maybe future commercial options for launching Robonaut parts, upgrade parts in the future.
Thank you. Hi, Greg Dobbs with HDNet Television.
Hi, Greg.
2 questions, please. Number one, the long-term task goals. You talked about what it can do, and those are really tests to utilize it in the station. But deeper into space, you said generally maybe it will enter worlds that are unexplored before man goes in. Can you be more elaborate about your long-term goals and long-term capabilities?
So for robots that are designed to work with humans, there are really 3 phases of exploration. The first phase is where the robots are out ahead of the humans. Then the second phase is while the humans are at the same site, the robot's working with humans. Typically, those phases of a mission would be short, maybe weeks or months. And then either in between human crews, going back to the same site, or where the humans never return to that site. In either case, the robot would be left behind as a caretaker to run longer-term experiments, maybe set up by the crew and then tended by the robot. So those are really the 3 phases where a robot could help humans as precursors to human missions, during the human phase of the mission, and then following human phases as caretakers or experiment tenders. This robot with different lower bodies is applicable to many destinations. We're obviously starting with in space, where it's going to be working in a zero-G environment, zero-gravity environment. We've been testing them to date in a 1G Earth gravity environment. So basically any planet with gravity up to Earth's, we think we can handle. So that would include Mars and the Moon, and certainly any asteroid. The robot is obviously strong enough to handle objects in 1G and would be quite capable in 0G, the microgravity of an asteroid on the lunar surface or on the Martian surface. So those destinations are ideal for this robot based on the way it's been designed. In each case, we would probably want a different lower body. So again, we're more focused on the upper body, the part that does work, and we're looking at different lower body options that can be used to customize it to the specific destination.
And the question about power, it's not going to have scrambled eggs every morning. What will power it? What will recharge it? Is it exotic or is it fairly conventional?
Well, at this point, it's really simple. It has no stomach. It's amazing what a human can do on one Hershey candy bar, right? It's a lot of energy in that Hershey candy bar. This robot has no battery or storage, so it's plugged in. Its backpack is an adapter that adapts from the station flavor of power to all the different voltages and currents that the robot needs inside. To go free climbing, we need to swap the backpack out with a new backpack that would have a battery or some other energy source that could then go recharge itself. That would also be the ideal backpack for going outside as well, where it would be able to work for some period of time unplugged and then get back in time to plug itself in and recharge. If it's plugged into a rover, it may need no backpack at all. If the rover is designed to provide just the right flavor of power to the upper body, it may need no backpack and be able to plug right into the rover's power supply.
Hi, Mark Kirkman, Interspace News. I actually have a million questions, but I think Brandy's only going to have a couple. Where on station will R2B be located at?
In the U.S. lab.
In the U.S. lab. And I assume you've tested in the VR lab the ability. Does he have the ability to get anywhere on the station using just the 2 arms?
We're not planning to have it free climb with just 2 arms. Our plan is to add legs so that it could climb in a very slow and deliberate manner. The pedestal that you see over on the display there is designed to go into the seat track on the side walls of the space station lab. What we are thinking, and we're open to ideas, but what we're thinking is that we'll build feet, modular feet on these legs that will be able to grip the various interfaces that exist on the inside of the station. So if you had 2 legs, one could be locked in and the other could reach out make contact, rigidize, and then let go of the other one. That would free the upper arms as it's climbing to be carrying objects, carrying wet wipes or carrying tools as it's climbing around the station. So it's kind of like rock climbing, but in rock climbing, you're typically hanging on your fingers with gravity, and you're not really making a firm, rigid interface to the rock. You're just kind of hanging. In zero-G, you have to make a more complete grasp of the object because there's no gravity bias. So the feet will need to be able to lock in to those seat tracks to stabilize the upper body as it climbs.
And then I guess this will be my last one. Can you elaborate a little bit on how those sensors work? I mean, are they specifically force feedback sensors in the joints, or do you have stuff within the skin? Because it seems like, and I half jokingly say this, that you guys have put a lot of emphasis on Asimov's 3 laws here, trying to make sure that there's no way that he can hurt an astronaut or vice versa. Can you explain how those sensors work with a little more detail, if it's not proprietary?
We have a lot of intellectual property that is coming out on the robot. We've filed over 40 patents. And so that will be coming out, and you'll be able to read about the patents. That's the nature of a patent, without giving away any of that information until the patents are filed. I can tell you that there are hundreds of sensors in this robot. And going back even to the Robonaut 1, there were 150 sensors per limb. So these are very sensate robots. With the Robonaut 1, we went through 4 different gloves with all kinds of skin-embedded tactile sensors, evolving the glove through 4 generations of gloves. We experimented with sensors under the skin to detect people. And in this design, the sensors are I could only say, more deep, that they're in the core of the machine, so we're able to detect the loads. But yes, sensing is very important to the machine. Hundreds of sensors throughout the whole robot. The control loop rates are thousands of times a second, monitoring those sensor signals and looking for accidental contact to make the robot safe. Our 3 levels aren't exactly Asimov's 3 laws, but we think that 3-layer safe is the way to go.
Okay, I think next we'll take some questions from Kennedy Space Center in Florida.
Yes, hello, Marcia Dunn with the Associated Press. First question I have is cost. How much money has gone into the Robonaut program, and how much is this individual robot worth by itself?
We think that about $2.5 million is the unit cost. I've never had the privilege of building robots in large quantities, so I'm not an industrial engineer. So I couldn't give you a better number than that for the case where we might make dozens or hundreds of these robots. But I can tell you, when I look at a Robonaut 2 and I look at my family car, the Robonaut has fewer parts, it has less material, and it seems that if you were to make Robonauts in the same quantities as you make that car, that the Robonaut should cost a lot less. Now, again, I'm not an industrial engineer, so don't take that estimate to the bank. But in quantities of 1 or 2, Robonaut 2s cost about $2.5 million.
Thank you. And another question I have is this the only Robonaut that will be flying to the space station? Or will you plan to fly another entirety to go outside? And if this Robonaut is the only one, or there are more to follow, will they all go down with the station eventually, or would you might hope to bring them back one day?
Well, so a couple questions there. Let me answer the first. At this point, we only have plans for this one, that we will look to fly upgrade components to the station. For example, giving it legs or a new backpack or a new torso computer. We would love to fly more in the future. We're looking at all sorts of missions beyond low Earth orbit, where the dexterous capability of a Robonaut system might come in quite handy. The second part of your question was, will it come home? At this point, we have no plans for Robonaut 2B to come back. I can't say what the future will hold. It may, ride the station into the Pacific, but we don't know where the station might go someday. So that chapter in Robonaut's life has not been written yet. We might take the robot, maybe that same one, beyond low Earth orbit in the future. It's got to earn its stripes first, though.
And lastly, is there any real-time control needed of Robonaut, or is this all programmable? In other words, if you need the robot to wash down the walls or the handrails, how do you get that command into the robot, and how much interaction from that point on is there with any crew or ground member?
So when we started working with General Motors, we went away from the teleoperation model that we had for the Robonaut 1. For GM, it really didn't make sense to have a person have to teleoperate the robot doing a task. That wouldn't really buy you anything. So we wanted to build the machine able to do tasks on its own. So again, working with General Motors, we built a really nice interface, software interface to the robot that is essentially script-driven. Now the robot itself is very sensate, and it's sensing forces, it's reacting to forces, it reaches out and grabs objects, and it feels when it grabs them. But all of that is automatic. You start the script, it reaches till it feels the forces and does what it needs to do on its own without direct teleoperation.
Okay, I think that's actually about all we have time for today. We can find out more about Robonaut online at www.nasa.gov/Robonaut. There's a fact sheet there, as well as videos and photos. Coming up next on NASA TV, we'll have a quick look at some more B-roll for the STS-133 mission. And then at 2 p.m., we'll wrap up today's pre-flight briefings with the STS-133 Crew News Conference. All that's coming up. Until then, thanks and have a great day.